Today we're going to look at graph product powers and the limiting behavior of their densities and sizes. To review, a graph product is a binary operation on graphs that takes as its input two undirected graphs and outputs an undirected graph whose vertex set is the Cartesian product of the input graph vertex sets and whose edge set is defined by some so-called adjacency rules. For example, we could define the rule that an arbitrary pair of vertices uv and u'v' in the product graph are adjacent when u is the same vertex as u' in the left input graph and v is adjacent to v' in the right input graph. What this particular product does is copy the right input graph once for each vertex in the left input graph. We can now define a graph product power. Given an associative graph product, the graph product kth power is what we get when we multiply this graph by itself k times. We'll define the first power to be the graph itself. Note that if we have a particular symbol we are using for our graph product, say the Cartesian product and the box symbol, then we denote the graph product kth power as g exponent the symbol for our graph product, comma k. As an example, let's take the third Cartesian product power of the graph G shown here, the complete graph on three vertices. The graph Cartesian product of G with itself is shown here. Next, we take the Cartesian product of that graph with G. This is our result. Moving on, let's investigate four different product powers more deeply. Specifically, those product powers formed from the most commonly studied graph products, the Cartesian, Tensor, Strong, and Lexicographic products. The adjacency rules for these four products are shown above. Recall that we have expressions for the size or number of edges of the product in terms of the sizes of the input graphs. We can now use those expressions to obtain recurrence relations for the size of the kth power in terms of the size of the k-1th power of some graph x. Let's first define the sequences v and e, where v sub k is the number of vertices of the kth product power and e sub k is the number of edges of the kth product power. Since we have associativity, we can choose to perform the operations from left to right without changing anything. So the kth product power of our so-called base graph equals the product of the k-1th product power with the base graph itself. Starting with the expression for the Cartesian product, we get the following recurrence relation, with v sub h replaced by v sub 1 and e sub h replaced by e sub 1, as the right graph in this case is simply the base graph, and v sub g is replaced by v sub k-1 and e sub g replaced by e sub k-1, as the left graph is the previous product power. We can apply these same substitutions to the rest of the expressions to get recurrence relations for the size of the kth power for all four of our products. Next, notice that for all k, v sub k is v sub 1 raised to the kth power, because the vertex set of the kth power is the set Cartesian product of the original vertex set with itself k times. So we can replace v sub k-1 by v sub 1 to the k-1th power. From the recurrence relation for the tensor product, we can see that each successive term is multiplied by a factor of 2 times e sub 1, and the first such multiplication happens from k equals 1 to k equals 2. So the explicit formula for e sub k must be 2 to the k-1th power times e sub 1 to the kth power. For the Cartesian product, if we use the recurrence relation to write out a couple of terms, we can quickly guess that e sub k should be k times v sub 1 to the k-1th power times e sub 1. It's straightforward to show that this is true using induction. For the lexicographic product, we can again use the recurrence relation to write out a couple of terms, allowing us to quickly guess that E sub k should be this. For the strong product, this method doesn't work as well. There's no clear pattern to the coefficients in the expanded expression for E sub k for different k. However, we can find a pattern if we write the recurrence a bit more generally. The recurrence relation is of the form E sub k equals c times E sub k minus 1 plus f of k, where f of k and c are as shown here. We want the recurrence to start at E sub 1, which is the same as f of 1. By our recurrence, E sub 2 equals f of 2 plus c times f of 1, and E sub 3 equals f of 3 plus c times f of 2 plus c squared times f of 1. And there's now a clear pattern. The solution seems to be the summation shown here, which I encourage you to verify for yourself. We can now substitute the original values for f of k and c to get this expression for the size of the kth strong product power of a graph. All in one place, these are the expressions for the sizes of the product powers of the four most common graph products. Note that we've rewritten the expression for the lexicographic product because it's a geometric series. Moving on, notice that the size grows very quickly. We can see that the lexicographic and strong products are going to be the products where we see the fastest growth in size. Next, let's look at the density of product powers. Recall that density is the size divided by the maximum possible size. Or for the kth product power of a graph, it would be E sub k divided by the following expression, which is the maximum number of edges in the kth product power of the graph. Intuitively, this quantity grows like v sub 1 to the 2k, so we can quickly see that the density will tend to 0 for the Cartesian product, whose size only grows like k times v sub 1 to the k. Next, the tensor product size is less than or equal to the size of a strong product. So we might be able to save some work and answer the question of the limit density for the tensor product by answering the question for the strong product. The size of a strong product power, which grows like 2 times E sub 1 plus V sub 1 to the k, can only grow at the same rate or faster than the maximum possible number of edges if 2 E sub 1 plus V sub 1 is greater than or equal to V sub 1 squared. However, E sub 1 is at most V sub 1 times V sub 1 minus 1 over 2. So 2 E sub 1 plus V sub 1 is at most V sub 1 squared. This occurs exactly when the base graph is a complete graph. For this case, the density remains fixed at 1 because a strong product of a complete graph stays complete. In all other cases, 2 E sub 1 plus V sub 1 is less than V sub 1 squared, and in the limit the density will go to 0. This tells us that the tensor product density will also go to 0 in the case of a non-complete base graph. And in the case of a complete base graph, we can simply plug in the number of edges of the complete base graph for E sub 1 in the formula to see that E sub k also goes to 0 in that case. The lexicographic product power, whose size grows like V sub 1 to the 2k, does not have a limit density 0. Instead, it actually remains the same as the density of the base graph. We can see that this is true by dividing the expression for the size of the kth lexicographic product power by the maximum size of the kth power to see that we get a constant expression. Interestingly, the lexicographic product is the only one of the 4 commonly studied products that keeps density fixed as we take higher and higher powers. For fun, here's the comparison between each of the 4 commonly studied products of the first 3 powers of a path graph on 3 vertices. Notice how much sparser the Cartesian and tensor product powers are. And remember that we started with a pretty dense graph, The path graph on 3 vertices has 2/3 of the max number of edges possible. And this high density is more striking when you look at the third power of the lexicographic product. As the last topic in this video, let's move beyond the 4 most commonly studied products and think about graph products in general. A graph product is determined by a selection from among a set of 8 basic adjacency rules shown here. The Cartesian product is what we get by selecting the first and third rules, the tensor product by selecting the fourth rule, the strong product by selecting the first, third, and fourth rules, and the lexicographic product by selecting the first and third through fifth rules. The set of edges produced by a given rule are disjoint from the set of edges produced by the other rules. All graph product kth powers will have the same number of vertices, v sub 1 to the k, where v sub 1 is the number of vertices of our base graph. It's only in their edges that they differ from each other. Now recall our previous table. Any graph product that includes the lexicographic product as a subset, which we can define to mean it's superior to the lexicographic product, that is, this is any product that chooses at least the first, third, fourth, and fifth rules, will have the property that the density does not go to 0 as we take higher and higher powers of the base graph. This is reflective of a general fact about superior products, which is that a superior product power will have at least as many edges as an inferior product power, and therefore will have a density at least as high as that of the inferior product power, provided both product powers use the same grouping of operations, in the case that the products are not associative. Since inferior products have density less than or equal to their superiors, any product inferior to the strong product will have density going to 0 for the kth product power for non-complete base graphs. In this way, we can say something about the behavior of the density of kth product powers for many more products than just the 4 we studied in this video. Interestingly, there are products for which the density increases as we take higher product powers. For example, a product just slightly superior to the lexicographic product, with the inclusion of a single adjacency rule, appears to increase density as we take higher product powers, where we choose to carry out the operation from left to right. That's all for this video. Thanks for watching.